Q&A session immediately after the video playing, and we expect the presenting author and also other authors, if possible, to join the session. And if especially the presenting author should be there, because otherwise we will consider it as a no-show case. So I hope that at the beginning, when I nominate, mention the names, the presenting author can give a signal that he is present, and we can see them. Okay, with that, I will move on to the conduct of the session, because we have to be timely on our session to conclude it in time for the other proceedings of the day. The first presentation lined up is electric regenerative hybrid system for the traditional auto-rickshaw. And the authors are Himani, Bisht, and Ganesha, Udupa. And I don't know which one is the presenting author.
Sir, Himani Bisht here. I'm going to present.
Okay. Good. We are joining from India. Okay.
India.
Yeah. Good morning to you.
Morning.
The session. Okay. Okay. So we can now listen to the first presentation.
A very good morning to all present in the virtual conference. I am Himani Bisht from Department of Mechanical Engineering, Amrita Vishwa Vidyapeetham, Amritapuri, India. Going to be talk about on my research title, Electric Regenerative Hybrid System for a Traditional Auto Rickshaw. My co-author is Dr. Ganesha Udupa from Department of Mechanical Engineering, Amrita Vishwa Vidyapeetham, Amritapuri, India. These are the outlines that I will go through in details in the upcoming slides. As we all know that the traditional auto rickshaws are a popular means of public transportation, but they also contribute significantly to air pollution. Also, recent studies have shown that the traditional auto rickshaws are still in use in large numbers, and they must be upgraded to hybrid auto rickshaw. Many small manufacturers and major players such as Bajaj, Mahindra and Piaggio produce e-rickshaw, but none of them are operating on regenerative hybrid auto rickshaws. If no regenerative framework is present in the e-rickshaw, the battery needs to be charged for 6 to 8 hours after 80 to 100 kilometers. This study aims is to design a cost-effective electric regenerative hybrid system for traditional auto rickshaw that does not require any major structural changes. The electric regenerative hybrid system would be capable of operating the auto rickshaw in two modes, electric mode and IC engine mode. Since the standard Bajaj auto rickshaw already has an electric engine running in the IC engine mode, the simulation of auto rickshaw in electric mode was run on the MATLAB Simulink platform to look at the battery and vehicle output and compare result with our mathematical calculation model for the validation. These are a few study papers that I have used to gain some insights into previous research work. In the first paper, they have used hybrid vehicle drive system, which is having two generator motor unit and engine starting means. In the second paper, they are using differential based VSD, and in the third, design and manufacture of Amrita Surya Vahini, a solar auto rickshaw. The operation of an electric regenerative hybrid auto rickshaw can be understandable with this functional block diagram. In electric mode, the generator motor 2 GM2 is only used as a driving source of power to drive the vehicle, while the generator motor 1 GM1 is in non-load mode. The engine itself drives the auto rickshaw in IC engine mode, while the generator motor 1 is utilized as an electric generator by the engine to charge the battery. Also, generator motor 2 will be kept in the non-load state, allowing the motor shaft to rotate freely. These 2 points I have already explained, that how the system is going to be work in the electric mode and in the engine mode, and how the regenerative framework is going to be work. Designing of a BLDC motor. Our research vehicle is a Bajaj auto rickshaw with all specification obtained from the company's website. The rolling resistance of auto rickshaw on asphalt is 131.84. The force necessary to overcome air resistance for an auto rickshaw with a drag coefficient of 0.29 and a frontal area of 2.2 square meter traveling at 50 km per hour can be calculated, and the value is 0.738 kilonewton. The required power in electric motor for auto rickshaw driving on a flat surface with constant speed 50 km per hour with an aerodynamic resistance for 73.84 Newton and rolling resistance for 131.84 Newton, and overall efficiency will be 3.36 kilowatt, and the torque value is 8.91 Newton meter at the rate 3600 RPM. So these are the values we got from the mathematical modeling while designing a BLDC motor. We computed the battery capacity and power of an electric regenerative hybrid auto rickshaw using a 3.36 kilowatt BLDC motor. For our hybrid auto rickshaw, we are developing a 48 volt 60 ampere hour battery pack. So battery pack will be 48 volt 60 Ah. So for 48 volt we need 15 cells in series, and for 42 Ah we need 10 cells in the parallel. So the total cells required is 150 cells. So these are the calculations. The total cells required is 150 cells. The uniformity of lithium ion batteries has a significant impact on the battery pack longevity and protection. As a result, it is crucial to assemble the batteries in a pack with a high level of consistency. As a whole, the cell sorting shown here is extremely important. To achieve the voltage and current needed for the power pack, all cells are connected in series and parallel. To get 48 volt, 15 cells should be connected in series and 10 cells should be connected in parallel to get 60 Ah. So this is the module preparation, and this is the battery pack with LiPo 415S 48 volt BMS. The BMS we are using, having the specification, is 15S 48 volt. Designing of mechanical power distributor. As we all know, the power split device is an important component that influences the power system control strategy, fuel economy, and vehicle dynamic efficiency. So in order to reduce the cost of a device, a differential based design has been used for power delivery. So this is the MPT layout. So we can see that in engine mode, in this mode only the engine is operated as a drive power source to drive the vehicle, while the generator motor 1 is operated as an electric generator by the engine to charge the battery, and the GM2 is placed in its non-load state, and the second is electric drive mode. So here only the GM2 is operated as a drive power source to drive the vehicle, while the GM1 is placed in the non-load state. This is the simulation model. Since the standard Bajaj auto rickshaw already has an engine running in the IC engine mode, a simulating model of a hybrid auto rickshaw takes the drive cycle as input and output. A graph in electric mode that validates the result for the proposed mathematical model has been implemented. FTP75 drive cycle and another constant signal block were applied. Results. This figure shows the vehicle model moving at a constant 3500 RPM. The battery voltage rises at 51.2 volt and drops to 50.8 volt after 35 km. This is voltage, distance, RPM versus time graph. This is voltage, distance, RPM versus time graph with regenerative braking. So we can see from the figure that auto rickshaw running with FTP75 drive cycle. Due to the regenerative braking, when the brakes are engaged, the motor RPM reduces and the battery voltage rises. This is SOC versus speed graph. The figure is depicting an auto rickshaw traveling at a constant speed of 48 km per hour with the served battery drain from 90% to 40%. This is SOC versus speed graph. This is SOC versus speed graph with regenerative braking. So when we are applying regenerative braking, the battery is charging. When the auto rickshaw is running on the FTP75 drive cycle on variable speed with the brake applied, as a result of the regenerative braking, the battery is charging. This is current versus speed graph. So as per the mathematical model, the motor can draw maximum current of 70 ampere. So in this graph, motor draws 49.8 ampere when the auto rickshaw is traveling at a constant speed of 48 km per hour. This is current versus speed graph. The motor draws 49.8 ampere when the auto rickshaw is traveling at a constant speed of 48 km per hour. Torque versus speed. The figure indicates that while an auto rickshaw is traveling at a constant speed of 48 km per hour, the motor torque is 8.91 Newton meter. This is a comparison table of mathematical results that we got from the calculation versus the MATLAB simulating results which we got from the graph. So as we can see that the results are fine, satisfactory for us. We can compare the value. A hybrid electric system for a traditional auto rickshaw is built in this research work by integrating and combining a differential based mechanical power distribution device, 2 BLDC generator motor and a lithium ion phosphate battery pack. For design verification, a mathematical model is also simulated in MATLAB Simulink. Simulation finding reveals that the suggested innovative hybrid electric system for auto rickshaw can travel 60 to 80 kilometers at a cruising speed of 30 to 35 kilometers per hour, while fully powered by a lithium ion phosphate power pack that can be charged electrically while the vehicle is in IC mode. IC engine. Future work. This research work along with development of hybrid electric system will bring the hybrid electric auto rickshaw onto the road in near future. Thank you.
Okay, coming to the end of the video presentation. Is Dr. Ganesha also present now? Or?
No, sir, only I am present.
Okay.
Himani, Bisht, only I am.
Himani is there. So we can have, we have 3 minutes for the Q&A, so we can have a couple of questions. May I myself ask a question, Himani, that we saw the battery, the lithium ion battery cells that you are using, they appear quite uniform, but one of the problem with the Leaf and other cars is how to get these cells. But now you have used standard cells available in the market. And you said they should match very well to optimize the battery pack. So if you buy from different manufacturers, will there be, now later on, if you want to replace one cell from a different manufacturer, will there be a significant characteristic change?
Okay, can you repeat your question? Actually, it's not clear.
Cells, now when you connected the cell, you said that they have to match very well. So you are testing them before making the pack. And so if you buy a cell from a different manufacturer, will there be a significant difference in matching the batteries?
I don't think so, sir, because the specification is going to.
Can I ask a question related to that? Now, when you say matching, how close do you mean matching? What voltage range would you consider as battery is matching, and what sort of internal resistance or whatever else that you consider for matching purposes? Because even a slight difference in voltage will have a large circulating current.
So matching in case like if if we want to connect cells in series, for that like as I have to care 48 volts 68, so for that we need 48 volts. So, I think there in case we need matching. I don't know what matching you're asking for.
No, you mentioned that lithium ion batteries are matching very well. Now, one of the problems, as the chair asked, when you buy batteries, unless they are very high quality, there's going to be slight differences in voltage. Even if you take 2 lead-acid batteries, depending on how old they are or what state of discharge they are, the voltages are different. Then there are circulating currents. So when you said they are perfectly matching, did you consider the tolerances in the batteries?
Okay, maybe it's because of the time limitation, we will wind up the discussion. Possibly you can communicate. It's very interesting. So we can maybe email, communicate, and discuss further if required to share more knowledge. Okay, thank you very much, Himani. And, nice presentation. Okay. Then we will move on to the second presentation today, titled SOC level estimation of lithium ion battery based on time series forecasting algorithms for battery management system. Authors are Dinidu Jeewandara, KTMU Hemapala, and JP Karunadasa. So, who is the presenting author? Dinidu, is that to you?
Yes, sir. Yes.
Okay. Okay. So let us go through the video. Okay, let us go through the video. Okay.
Well, have a safe and pleasant day, everyone. I am Bindu Jeewandara from the University of Moratuwa. My research is a source level estimation of lithium ion battery based on time series forecasting algorithm for battery management system. Okay, this is a small introduction about battery management system, or we can say the BMS. A BMS is an electronic system which can manage the rechargeable batteries in proper way. And you can see the sum of the function of BMS: battery modeling, battery state of charge estimation, battery state of health estimation, battery cell balancing, and battery thermal management. Actually, my research focus area is the battery modeling and battery state of charge estimation. For the battery modeling, we need to identify the battery parameters. So I'm going to propose a comprehensive electrothermal battery model and the battery parameter identification process. Mainly these battery parameters are dependent on the battery SOC level and battery core temperature. So that is why we need to estimate the battery SOC level very accurately. For that, I am going to propose a method. It is based on the SOC level estimate. It is based on the time series forecasting algorithm to estimate the SOC level. Okay. This is the proposed electrothermal battery model. In this battery model, there are two parts available. The left side one is the electrical model, right side one is a thermal model. This is a combination of electrical model and thermal model. In the electrical model, we need to identify the 6 electrical parameters. You can see the R1, R2. R1, C1 mean actually activation, polarization, resistance and capacitance. R2, C2 we call the concentration, polarization, resistance and capacitance. And the R node means series resistance, so we can say the internal resistance, and the VOC mean open circuit voltage. All of the 6 parameters we need to identify. The thermal model, we need to identify the 4 thermal parameters. RC, RU mean actually thermal resistance, CCCU mean thermal capacitance. For each of the battery parameter identification process, we need to estimate the SOC level very accurately, because mainly these electrical parameters are dependent on the battery SOC level and battery core temperature. Okay, so this is the thermal model. I use two-state lump thermal model. In this thermal model, to identify the thermal model parameters, we need to perform the constant current, constant voltage charge test, or constant current discharge test we can use. CCCV charge test or CC discharge test. Actually, you can see the first and second are the thermal equation. This thermal parameter identification process, actually, I'm not going to explain in detail, but simply you can see by comparing the measured core temperature and the calculated core temperature, we can calculate the thermal model parameters by utilizing the least square method. There's a method actually. I'm not going to explain in detail. However, it's okay. Then this is the electrical parameter identification process. For that, I am going to use the pilot discharge experiment. Actually, this is the usual pilot discharge experiment, the flow chart of the pilot discharge experiment. From this method, after the pilot discharge experiment, we can get this battery voltage time variation, this experimental variation. From this battery voltage time variation, we can easily calculate the series resistance and the battery open circuit voltage. We can directly calculate. To calculate the other 4 electrical parameters, that means R1, R2, C1, C2, we can perform this MATLAB curve fit in no optimization tool. That's a method. So today my research is the real-time SOC level estimation of lithium-ion batteries for battery parameterization procedure. So I'm going to find the SOC level accurately for each of the battery parameterization process test. So in this method, actually first after getting the data from the lithium-ion battery, that means for the CCCV charge test, CC discharge test and power discharge test, after getting the data, first stage is the data pre-processing stage. I will explain the data pre-processing stage later. Then we can separate the data set into the three subsets: training data set, validation data set and testing data set. Then by using this data set, we can create the algorithm. I use 6 kind of algorithm in this research: AR, MA, ARIMA, SARIMA, LSTM and NARCS. In here actually AR, MA, ARIMA, SARIMA all are time series forecasting algorithm, machine learning based concept, and LSTM and NARCS are, those are also machine learning, but I got from those from the deep learning architectures, neural network methods. However, after training the model, we can calculate the performance indices. That means mean squared error, root mean squared error, mean absolute error. You can see the right side, and the mean absolute percentage error and R squared error. I think you know the definition of these performance indices. And also I calculate the computational time, because in the real-time condition, performance indices as well as the compute time also very imperative. Okay, then by checking the PI and CI values, I can ensure the what is the most accurate method for the each of the test which I perform in the battery parameterization procedure. Okay, and this is the data pre-processing stage. In the data pre-processing stage, first stage is the most imperative part is the decompose the data set. By decomposing the data set, we can select the which forecasting model is more suitable for the data set. By decomposition, we can get we can identify the data set trend, seasonal variation, cyclical variation, random or irregular variation. Trend mean actually, you know, some data set has increasing trend, some has decreasing trends, like that. The seasonal variation mean actually the same value is repeated several times in the data set. Likewise, we can find this level of the data sets. It is based on the time series forecasting algorithm. That means if we have only trend lines, then we have a separate time series forecasting algorithm for that. If we have only seasonal variation, then we can have another time series forecasting algorithm. Likewise, we can select the most suitable time series forecasting algorithm for that. And the second important point is the stationarity. Actually, stationarity mean actually the statistical properties of the data set, like mean, variance, autocorrelation, do not change over time. Actually, each of the accurate time series forecasting algorithm are stationary. So that's why we have to check that one. For that, we can perform the augmented decay Fuller test, or we can say the ADF test. Simply we can perform and we can identify the stationarity of the data set. But if we accidentally get a non-stationary data set, then we can use detrending, differencing, or other phenomena to stationarize the data set. Okay, this is a data pre-processing stage, and this is the use stochastic time series forecasting models. AR mean auto-regressive model, MA moving average, ARIMA mean auto-regressive integrated moving average, SARIMA is the seasonal auto-regressive integrated moving average. Actually here AR mean actually we can identify the future forecasted value by a linear combination of the past observation. In the moving average method, we can estimate the future value by a linear combination of the past observed error values. And the auto-regressive mean is a combination of AR and MA. SARIMA is a kind of ARIMA method, but it is used for the seasonal variation data sets. Okay, and these are the deep learning algorithm I studied. There are mainly 4 kind of deep learning algorithms. We have deep neural network, recurrent neural network, deep belief network, and deep reinforcement learning. Mainly I use recurrent neural network because in the recurrent neural networks we have a feedback connection, no memory capacity sometime, so we can memorize the past observation, then we can get the very accurate result. Here I use the NARCS and LSTM architecture. NARCS means nonlinear auto-exogenous network, LSTM means lone short-term memory. In the NARCS algorithm, we have two kinds of architecture, series parallel and parallel architecture. Parallel architecture. More suitable is the parallel architecture because it is more accurate than the series parallel architecture. So I use parallel architecture, and these are the result of the this research for the constant current, constant voltage charge test. You can see the performance indices and the computational time for each of the time series forecasting algorithm, ARMA, ARIMA, SARIMA, NARCS and LSTM. Based on the CI and PI values, I can select the what is the most accurate algorithm for the source level estimation for the CCCV chart test. According to the result, the AR model I selected as the best model for the source level estimation for the constant current, constant voltage charge test. You can see the compressed time and the performance indices variation. And the second graph table is for the constant current discharge test. Here also actually SARIMA model is the most accurate model. You can see the performance indices, but when we consider the computational time, that means in real time condition, most best method is the AR method. And for the pulse discharge experiment, here AR, MA, ARIMA, SARIMA all are very accurate, but if we consider the real time condition, then MA model is the most best model I selected from this study. Okay, and these are the experimental result of the time series forecasting technique. That means the graphical representation of the each of the charge and discharge tests, SOC level variation. That means I'm going to compare the measured SOC level with the experimental SOC level with the other estimated SOC level from the time series forecasting algorithm. And also the right side you can see the error variation for the each of the time series forecasting algorithm. So for the CCCV chart test, CC discharge test, and also pulse discharge test, you can see the result. Okay, well, this is the things I need to explain for this research, and these are the references I use for this study. And okay, thank you very much. This is end of my presentation, and if you have any question, this is time for that. Thank you.
Okay. Now we will move to take a few questions. It's open for questions now.
Can I ask a question?
Yes.
Now,
yes.
these batteries are going to be used for what purpose? Because one of the problems I have is, for example, let's take a phone.
Yes.
The state of charge that is shown, if when the battery is old and when the battery is new, are not the same result.
Yes, actually,
So are you taking those into account, and did you validate using not just charging and discharging, but using an actual system?
No, sir. Actually, here my focus is the battery parameterization. That means I'm going to propose a battery model. Then for the microgrid, actually microgrid battery management system. Then actually I validated by experimentally developing a test bench and experimentally finding the battery parameters.
No,
that is
the problem is when you do it in a uniform manner, the results will normally be good. But
yes,
when there are, for example, a phone, I know when you talk a lot, the charge discharges very much faster than when you don't use the phone. So this static methods of steady discharging or steady charging will always show good results.
Yes, yes. Actually, in that scenario, we have to we can't use this part. But here, actually, I only focus that that battery model. It is especially I didn't select for the mobile phones and those
just one comment. No, then you should have had the title, the battery modeling, because this is SOC level estimation.
Yes, yes, only for SOC level estimation.
Can I give some answer for that?
Yes, yes, Professor Karunadasa, yes.
Yeah, so this is exactly the purpose what Professor Lucas was suggesting. So when batteries are in operation, after some time the battery gets degraded and their parameters are going to change. So what this research is about, the reassessing the parameters parameters of the battery at the point of the state that we want to study and use those parameters in these particular algorithms to suggest the SOC. Therefore, it is a adaptive and predictive type modeling, and it will give a better estimate of the SOC for the present state of the battery.
Okay,
Thank you. I think that explained what I was asking about.
Yeah,
So,
one more quick question from me, that in the battery management system for this kind of applications, how it will differ from a situation like in a vehicle where burst of energy is going up and down. When you brake, it will be sending energy packets into the battery, and immediately when you accelerate, it will be taking the charge out of the battery. So in that situation, how challenging will be for the battery management system for these kind of estimation, the associated estimations?
Yes, actually, it is something different scenario. That means I didn't focus that part, but
Okay, it's not clear. Okay.
Yeah, I think those are transient considered transient conditions. They have not considered.
Consider not only this parameter part, not we have to, but also consider the thermal management part also. So and also the cell balancing part also.
Okay. Thank you, Dinidu. Okay, for the time we will proceed to the next title, and maybe others can interact with him using email and other chats for if you want more clarifications.
Yes.
Thank you. Okay. So we'll move on to the third presentation this morning, and that's also a nominated paper for the best paper award. So the title is Performance Evaluation of a Hybrid Dual-Axis Solar Tracking System. Authors are Kithma Vidanapathirana, Hansi Kumarapeli, Dineshi Marasinghe, Dulini Amarasinghe, and Joseph Rohan Lucas. And I understand Kithma will be presenting the video. Is Kithma present?
Yes, sir, I'm present here.
Okay, good. So let us go ahead with the video presentation.
Okay. Hello, everyone. I'm Kithma Vidanapathirana from General Sir John Kothalavala Defence University. Our research paper is about performance evaluation of a hybrid dual-axis solar tracking system. Moving on to the introduction, our work presents the design of a manual automatic hybrid dual-axis solar tracking system. This system is called hybrid because it tracks the sun using the automatic tracking mechanism as well as manual tracking mechanisms. And this system is dual axis because the solar panel rotates in two different axes to track the daily and seasonal motions of the sun, as shown in figure 1. This dual axis tracking eliminates the cosine error which occurs in fixed solar systems by tilting the panel towards the direction of the sun, which will ultimately eliminate the misalignment of incoming sun rays with the panel, as shown in figure 2. In the developed solar tracking system, daily east to west motion of the sun is tracked automatically using a stepper motor, and seasonal north to south motion of the sun is tracked manually using a gear wheel system. And also in the developed system, automatic tracking mechanism uses two control strategies such as time-based chronological tracking and light-dependent resistor-based active tracking. Various research has been done previously on solar tracking systems. In this table, we have categorized them according to the solar tracking method and solar tracking mode. The efficiency improvements obtained in each of these systems are included in this table as well. However, some of the previous research analyzed have not considered the seasonal motion of the sun, whereas in our system, we have considered both seasonal and daily motions of the sun. And all the dual-axis tracking systems proposed previously have used two separate motors to track the seasonal and daily motions of the sun, whereas in our research, we have utilized only one motor because seasonal motion is tracked using a manual gear wheel system, which makes our system unique from previous systems. Moving on to the methodology, since in our system, we track the seasonal motion of the sun manually, first we have to identify the optimum criteria to track the seasonal motion of the sun. For this determination and to identify the frequency of changing the seasonal inclination angle, such as changing the angle monthly, twice a month, or 4 times a year, the percentage loss of energy in each scenario was calculated with respect to the optimum case of changing the inclination angle daily. As per the percentage loss of energy obtained as indicated in table 2, it was decided to change the seasonal inclination angle monthly since it has a lower percentage loss compared to changing the angle 4 times a year, and it is cost effective compared to changing the angle more frequently. This calculation was done based on total solar radiation on an inclined surface, considering beam, diffuse, and ground reflected radiation, which are indicated in figure 3. And then we determined the monthly seasonal inclination angles. The declination angle of the sun and the latitude of the location was considered for this determination. As shown in figure 4, the monthly seasonal inclination angle changes as a cosine function throughout the year. Therefore, the total number of angles needed to be changed for the seasonal inclination is 7, as shown in table 3 for Sri Lanka. The mechanical design of this solar tracker. In here, the solar panel is connected to the daily motion shaft, and the daily motion shaft is controlled by a stepper motor based on instructions provided by the microcontroller. And then the seasonal motion shaft is controlled manually using a gear wheel system. And this is the experimental setup of the designed hybrid dual-axis solar tracking system. The solar tracker was implemented on a 150-watt solar panel. A 5 kilowatt fixed solar system was used for the comparison through scaling. It had 15 solar panels. Both of them were located at Polga, Sri Lanka. Based on geographical coordinates, the optimum tilt angle for the fixed solar panel is 6.79 degrees to the south from the equator. But the fixed system had a tilt of 10 degrees to the south due to the roof angle of the mounting. This difference led to the peak power output of the fixed system not occurring exactly at midday. In the prototype, a lightweight panel was used to replicate the 150-watt solar panel, and the actual solar panel was aligned manually with the lightweight panel when taking readings. Moving on to the automatic tracking system of the designed solar tracker, it is implemented using 2 control strategies, time-based chronological tracking and Ldr-based active tracking. So figure 9 shows the time-based chronological tracking algorithm. In here, the solar panel rotates to initial position from the horizontal rest position at 8 AM, and then panel rotates from east to west direction from 8 AM to 6 PM by an angle of 3.6 degrees once every 15 minutes. And at 6 PM, the panel is rotated back to the horizontal rest position. In LDR-based active tracking, a separate LDR sensor panel was implemented consisting of a total of 12 LDR sensors with 6 on either side of a barrier. The LDR sensor panel was mounted along with the daily tracking axis. To rotate the solar panel in the direction of maximum solar intensity, a parameter called moment was calculated by multiplying the analog intensity values of each LDR sensor with distance from the barrier. The control algorithm is given in figure 10. Manual tracking system of the developed solar tracker. In our research, a manual gear wheel system was used to track the seasonal motion of the sun. So the gear wheel system orients the panel by around 3 degrees for each tooth rotation. The months of the year are numbered from 1 to 12, and it is marked on the gear wheel, and it will be aligned with the reference arrow manually every month for seasonal tracking as indicated in this figure. Moving on to the results obtained from the developed hybrid dual-axis solar tracking system, the performance of the designed solar tracker was analyzed with respect to the fixed system. The daily east-west motion of the sun was tracked throughout the day using the time-based chronological tracking mechanism automatically, and the seasonal north to south motion of the sun was tracked once a month manually. The output power comparison between dual axis and fixed systems is shown in figure 12. This is based on average readings taken daily from 22nd December 2020 to 2nd January 2021 from 8 AM to 6 PM. It is observed from the graph that power generated from the tracking panel is higher for a short time early morning and in the evening, as the fixed tilt angle corresponds to just before midday. It can also be observed that a higher efficiency improvement is in the evening, as probably the fixed panel is oriented for best performance in the morning. The average efficiency of the hybrid dual-axis solar tracking system compared to the 10-degree tilt fixed panel was 32.7% for this particular arrangement during the selected period. The performance of the hybrid dual-axis solar tracker was analyzed on a clear sky day, rainy day, and a cloudy day separately. A clear sky day was observed most of the time during the day, although there were some minor cloudiness in the sky at some times, which resulted in minor fluctuations in this graph. The efficiency improvement in the tracking system on a clear sky day compared to 10-degree tilt fixed panel was 35.7%, which was higher than the average value. Moving on to the output on a rainy day, when we look at the output on a rainy day, it can be identified that the power of the tracking system was nearly as same as the power generated by the fixed system from around 8 AM to 1:30 PM. The reason for this variation was because sun was not visible to the solar panel at that time. Due to that, the solar power was mainly generated from diffuse radiation of the sun rather than beam radiation. However, the sun was visible to the panel from 1:30 PM till 6 PM, so that the power generated within that time period is significantly higher compared to the fixed panel as indicated in the graph. The efficiency improvement on a rainy day was 31.5%. And then the output on a cloudy day. On this day, the sun was covered with clouds most of the time throughout the day. As indicated in the graph, the output power of both fixed and tracking systems has varied significantly throughout the day with major fluctuations. The fluctuations in both graphs were approximately equal as shown in this figure, although the power generated from the tracking panel was slightly high. The efficiency improvement in the tracking system on a cloudy day compared to 10-degree tilt fixed panel was 22.3%, which was lower than the average value due to sunlight dispersion due to the clouds. This table shows an average weather data for clear sky day, rainy day, and cloudy day considered in this study. Energy produced by tracking and fixed systems at different time intervals are indicated in this table, together with the efficiency improvement of the tracking system compared to fixed system. In here also, we can observe that there's a higher efficiency improvement in tracking system in the evening from 4 PM to 6 PM, as probably the fixed panel is oriented for the best performance in the morning. This proposed solar tracker has been developed aiming high capacity solar power consumers and for implementation on ground mounted solar systems. And finally, the conclusion. Our work presented a hybrid dual-axis solar tracking system which tracks the sun's daily east-to-west motion automatically and the seasonal north-to-south motion manually for economic reasons. The design solar tracker was tested and showed an improvement of efficiency of 32.7% compared to the fixed system. It is also found that the improvement in efficiency varies depending on the condition of the sky. On a clear sky day, it was 35.7%, on a rainy day it was 31.5%, and on a cloudy day it was 22.3%. So the benefits of the implementation of the hybrid dual-axis solar tracking is highest on a clear sky day, where the sun is visible to the panel most of the time during the day without cloud cover. However, further experiments need to be conducted to test the efficiency during different seasons. These are the references used for this presentation. And thank you.
Okay, are the other authors are also present? Hansi, Dineshi, and Dulini. I know that Professor Lucas is already there.
Yes, all of us are present here.
Good. Thank you for joining. And so we can take a question or two.
One question from me, Karunadasa. So when these tests were done, did you use two sets of solar panels, one with tracking and one without tracking for the test, or was it done simultaneously? How was it?
So we obtained fixed system readings from a already installed rooftop solar system, a 5 kilowatt system, and we obtained the readings simultaneously. Yes.
So was it similar system or dissimilar as far as capacities wise?
Can I answer that question?
Sure.
The capacities were quite different, but it was scaled down so that both became the same. So comparison is based on the same rating. They want adjacent buildings, so maybe so one was on the rooftop, and near there the manual one was also there.
But the experiment could have been done for the same kind of panel at the fixed angle as well, rather than using the rooftop and
no,
scaling down.
Practically, the rooftop gives accurate readings on a monitoring platform. So that was used as a basis to compare. Otherwise, simultaneously, the readings, when you take, you have to make sure that both, I understand, there are errors caused by that. So maybe about 5% or so error may be due to that. So where there are slight deviations, perhaps the two might have virtually coincided. But clearly in the evening, you can see quite a significant deviation. That is because probably in the morning, the panels were oriented for the correct direction. But since the panels were not rotated throughout the day, by evening, there was quite a variation, and that is shown on all days: clear day, rainy day, and cloudy day.
Okay, thank you all the presenters for the answers. We'll move on to the next, because of the time, we'll move on to the next topic, fourth presentation this morning. The title is Techno-Economic Assessment of Using Utility Scale Battery Storage to Facilitate Variable Renewable Energy Integration in Sri Lanka. The authors are Asit Kaushalya and KTMU Hemapala. So we can see the video recording now.
Hello all, I'm Asit Kaushalya, and I will present the conference paper on techno-economic assessment of using utility scale battery storage to facilitate variable renewable energy integration in Sri Lanka, which has been co-authored by Professor Udayanga Hemapala. First, I will give you a brief introduction of the study we have carried out. Sri Lanka is a country with abundance of renewable energy resources, which could be utilized in electrical energy generation at zero fuel cost. Long-term generation expansion plan of Ceylon Electricity Board, which is the main planning document in the electricity sector of the country, projects a considerable increase in renewable energy integration into the system over the next 20 years. In these renewable energy integration schemes, variable renewable energy, which can be considered as wind and solar energy in our system, plays a major role in the next 20 years. But these resources have inherent qualities such as intermittency and uncertainty, which presents numerous technical and economic constraints to the system. And in the recent years, utility scale battery storage systems have emerged as a possible solution to these constraints. I will briefly tell you about the qualities of variable renewable energy. Intermittency of these resources is a major factor to be considered, which can be broadly categorized as variability and uncertainty of the resources. Variability is present mainly in wind generation in Sri Lankan context, which presents a constraint with seasonal variation of the resource. There are high wind seasons and very low wind seasons in the same year. And uncertainty is present mainly in solar generation with second to second or hour to hour variation, which cannot be predicted happen in the solar PV generation outputs. So these two qualities are presenting various challenges to the system operators in the power systems. Main impact of these resources is the increment of operating reserves to capture these variation of these renewable energy resources. So these resources forces the system operators to change the generation levels of flexible generations available in the system to compensate for the continuous changes in these VRA generation sources. This leads to uneconomical operation of these flexible generators available in the system. And another problem of high renewable integration into the system is the renewable curtailments. Curtailment occurs when system operators reduce the output from wind and solar generators to manage the generation mix under various system conditions, such as low load instances or excess generation present in the system. So utility scale battery storage has emerged as a possible solution to these problems. And these battery storage systems are used in many facets of the power generation system. In this study, I mainly focused on providing generation reserves through battery storage systems. There are two main objectives of the study. First one is the assessment of on the reduction in renewable energy curtailments by introducing battery storage to the system and estimating the economic benefit derived from these curtailment reductions. And the second objective was comparing the use of conventional generators and utility scale battery storage to maintain the required level of operating reserves in economic and technical perspective. The methodology I adopted was, the first step was a comprehensive literature survey on worldwide use of battery storage in VRE integration related activities and how battery storage are used to provide generation capacity reserves in power systems worldwide. And the next phase was the data collection phase, mainly for the technical and economic analysis I was going to carry it out. I collected demand projection data, wind and solar resource data, and other plant parameter data, which are used to model the system to carry out the dispatch analysis and the resultant economic analysis. And the next step was the technical analysis on battery storage, which involved a detailed dispatch analysis to study the power system operation, effects on dispatch, and reduction of curtailments with the introduction of battery storage. And the last step was the economic analysis, which involved using the results of the dispatch analysis to assess what is the economic benefit and the related cost for the introduction of battery storage to the system as an operating reserve. Development of the model of power system using SDDP, which is stochastic dual dynamic programming, which is the main dispatch simulation software used for the long-term planning process in the Ceylon Electricity Board. I developed two scenarios: the base model with assigning operating reserves from 3 into 35 megawatt gas turbine power plants, which would be commissioned in Kalnithisa power plant by year 2022, and scenario 2 as an alternative model with assigning operating reserves from battery storage only and releasing the gas turbine power plants for the economic operation. For the battery storage, I used 100 megawatt hour battery storage from 2022 onwards, and this study was carried out for 10 years from 2022 onwards. And as for the results, first I will show you the reduction of curtailment of RE with the introduction of battery storage. These results are for a week in year 2024-2025 as a sample. As you can see from the top graph, with the introduction of battery storage, the curtailment levels are reduced significantly. And when I analyze the cause of these curtailment reductions, I clearly observe that net generation from battery storage caused these curtailment reductions compared to the case where operating reserves are provided by gas turbine power plants. So this is a benefit of introducing battery storage to the system. And next, the impact on the dispatch of gas turbine power plants with the introduction of battery storage. On the topmost graph, you can see in scenario 1, which is the batteries, gas turbines providing operating reserves. For the consecutive 5 days in May 2025, the output of the gas turbines are varying regularly to provide the balancing act with the variation of generation in the system. Then in the scenario 2, these gas turbines are released. So it goes back to the most economical operation, which is the acting as a peaking power plant. So only at the maximum output level, the gas turbines are operating at the maximum output level or zero generation level. So this is an economical output of the gas turbines. And when I check the battery net generation in the same set of days, they are providing the balancing act by acting as an operating reserve to the system. So this is an economical operation of gas turbines with the introduction of battery storage. And I did a basic economic analysis using the presented battery storage parameters and cost details, which are on approximately on 2018-2019 cost levels of battery storage I gathered from Lazard's report. And the results of economic analysis, I can present that these project would be marginally economical when benefits and costs are compared. A very insignificant net present value and a benefit cost ratio of just above 1 and a payback period around 7 years, which would consider as a marginally economical project with the current prices of battery storage. And as a conclusion, I can tell you that introduction of battery storage directly contributes to the reduction of variations of gas turbine power plant output, which leads to more efficient operation of the power plant. And also with the introduction of battery storage, PRE curtailment levels reduce significantly compared to the case with gas turbine power plants providing operating reserves. And also introduction of battery storage provides a comparatively robust source of operating reserves, which optimizes the hydro generation, reservoir-based and run-of-the-river, which drive the total operating cost of the system down. All these benefits are observed through this study. And as future steps of this study, I would continue the study on the sub-hourly advantage of battery storage, such as regulating frequency, provision of reactive power, and inertia support through softwares like PSSE or PSCAD. That's all from me. Thank you very much.
May I ask a question?
Yes, sir. I'm present. I'm Asit.
Yes.
Kaushal.
Okay. My question is, your economic analysis yields simple payback period of 7 years. So the benefit, okay, so the costs are the costs of bringing in the battery, and the benefits will be efficiency improvement in the gas turbine. Did you also include any benefits by way of avoided curtailment of solar PV?
Yes, sir. I also included both aspects, reduction in curtailments and the efficient operation of thermal power plants, both in the economic evaluation.
Fine. Then the benefit of avoided curtailment, how did you price the solar PV avoided curtailment?
That would be, sir, if in the curtailment values, I took the marginal cost of the system. If the curtailment values are, if the zero cost generation available through PV and wind are captured by battery storage, then the total cost of the system goes down. I evaluated it through the variation in marginal cost of the system.
Right. So you are likely to have curtailment during certain hours, and for those hours you calculated the marginal cost of the remaining, obviously, thermal generators of the system.
Yes. Yes.
And then valued that curtailments on to be equal to the avoided thermals, isn't it?
Yes.
Right.
Yes.
Okay. Thank you.
I think Professor Wijayapala's
you are muted.
mic
Yes.
is there.
Sorry, yes, sorry. Okay, now we will stop there for the questions because of the time limitations. And thank you, Asit, for the presentation and also the answers to the questions.
Thank you very much.
And now I will ask, yes, now I will ask Dr. Wijekoon, coach of this session, to take over and go through the next 4 presentations this morning. Dr. Wijekoon.
Yeah, thank you, Professor Wijayapala. So our next paper is paper number 5. That is the presentation, development of a cost-effective half-duplex power line communication system for low bandwidth home automation application. And authors are Satmini Jeewandara, Bopage Kumarapeli, Madhusanka Nishan Dharmavira, Bhatia, Vidanapathirana. And who is going to present, I think? Satmini?
Yes, I'm Satmini. I will be present.
Okay, okay. Right.
Hello everyone, I am Satmini Vaninayaka. The authors of this paper are myself, Umesha Kumarapeli, Dr. Nishan Dharmavira and Dr. Bhate Pilanavithana from Department of Electrical and Electronics Engineering of University of Sri Jeewandara. I will be presenting about the project on development of a cost-effective half-duplex power line communication system for low bandwidth home automation applications. I will be discussing on 6 sections, first with an introduction, then with a brief literature survey. Section 3 and 4 will be on the proposed solution and the results, and then the conclusion and future work. Smart homes are not a novel concept. The most popular automation mediums are Wi-Fi, Bluetooth, Zigbee, Z-Wave, and wired mediums like Ethernet. But there are some limitations in them. So as in the figure, in the future, the number of wireless devices connected will increase rapidly. Therefore, alternatives for radio frequencies might have to be used. When it comes to wireless mediums, due to blockages by walls and other reasons, interferences occur. This requires signal repeaters which add more cost. When it comes to wired mediums, need of newly laid channels creates the installation difficult in a built house. Further, users have to monitor regular battery replacements or other powering solutions. Also, some existing smart solutions are expensive. So we thought power line communication or PLC is a better solution for these issues. Our objectives are to design a cost-effective half-duplex PLC-based system for low bandwidth required applications like lighting and dimming. Devices can be protected for overcurrent by reading current sensor data, and with the use of PLC, this also can be accomplished. So this would require the system to communicate in both the directions. We require the system to be user-friendly with an easy plug-and-play installation. The electrical wirings are not meant to carry data, therefore channel noise affects immensely, and acquiring noise immunity is another objective of us. Also, the harmonics added from the system to the power line should be kept in a minimum level. So let's look at the literature briefly. These are some popular PLC protocols in the market. Xten has gained its popularity due to its low cost and installation. It is used by producers like Leviton, however, its immunity to noise is low. Insteon uses Xten, and a specialty in Insteon is that it uses radio frequency as a backup channel. It's an advanced proprietary protocol and it needs an initial installation process unlike Xten and Insteon. From the research, we found out that there are standards declared to PLC, and out of them, Senlec and FCC are popular standards. ARIB is used in Japan. When it's come to PLC, channel noise is a major factor that has to be considered. So, noise from CFL lamps and switch mode power supplies produces a noise of around 3 kHz to 40 kHz. Megahertz frequencies are used for radio broadcasting in most of the countries. Therefore, use of them will create interferences for radio broadcasting. These were considered in selecting a frequency range for our system. In most of the available products, OFDM is used for modulation, but it is costly. Amplitude shift keying is more prone to attenuation, therefore it is rarely used. Also, in some products, phase shift keying and frequency shift keying are used. Now let's have a look at our proposed solution. The proposed solution consists of a main controller node and multiple appliance nodes which are plugged to the electrical wiring through a power socket. The user is connected to the main node through a mobile app. So when the user operates the mobile app, the main node retrieves the commands, then the main node transmits these signals to the appliance nodes. Same way, appliance nodes transmit current data back to the main node. So in the system, a high frequency signal in the Senlec band is coupled to the AC mains voltage. For synchronization, we are injecting the high frequency signal at a zero crossing of the AC mains voltage, and 1 bit is transmitted at a zero crossing. This is a functional block diagram of the system. Each node consists of 4 major sections: main control unit, the analog front end, the signal coupler, and the input-output section. The input-output section consists of the zero crossing detection preprocessor, the current sensor, and the triacs. So when the I/O section gives the zero crossing detection preprocessor gives the signal, the MCU detects the zero crossings of the AC mains, and the transmitting or receiving of the bits are done at that time. When it is in the transmission mode, the MCU sends the bit value to the analog front end, and the AFE generates a high frequency sinusoidal wave according to the received bit. Then it is coupled to the power line. In the receiving mode, the signals are filtered out, amplified, and then fed to the MCU. Then at the zero crossings, the MCU detects the received bits and the decoded frames are sent to the I/O section to do the relevant actuations. We have used a low-cost general-purpose MCU. Therefore, in communicating with the AFE, due to the mismatch of the SPI blocks, the SPI communication have to be implemented manually. The MCU's inbuilt analog-to-digital converter is having a low sampling rate. Therefore, for sampling of the received signals, which are high frequencies, that was carried out using a timer capture method without using the ADC of the MCU. The channel noise impact, which would impact in the bit detection, was removed by fine-tuning the filter at the coupler. Further, the noises that were not susceptible to filtering were compensated using a correlation-based template matching algorithm. We prepared one main node and two appliance nodes and tested the system at different rooms of the house. So these videos show the two appliance nodes which are connected at different rooms, and the prototype worked as we intended. Bidirectional communication was tested by sending data frames from the main node to the appliance node and from appliance node to the main node. So we could observe that the frames were received correctly. We tested the system in a high noisy environment. So as you can see in the figure, these yellow signals are the high frequency received signal with noise. The blue signal are the recognized bit pattern, and it is clear that noise has not been misrecognized as a high bit in the received recognized bit pattern. These are the fast Fourier transform of the power line before adding the signal, and when the signal is added, we are sending a signal around 80 kHz. So from here we can see the noise added to the power line from our system. It is low. In concluding the project, we designed an based algorithm, and the harmonics added to the channel from the system is considerably low. So this system should be further developed for multi-phase networks using a suitable phase coupler, and also the bills of material count can be further reduced by using a current sensing IC and using the zero crossing detector which is in the analog front end. Also, the transportation layer has to be developed with the proper scheduling mechanism, and the data rate can be increased, which will increase the functionality. Last but not least, I would like to thank my supervisors, Dr. Nishan Dharmavira and Dr. Bate Pilanavithana. We also would like to thank Dr. Akila Subasinghe and Dr. Shamtadi Alvis for their support.
Okay.
Thank you very much for your
Thank
attention.
you. So we can have a few questions from the audience.
One question, Karunadasa, do you have a central unit at one location where this communication, where the signals are sent into the power line within the home?
Yes, sir. So the main node is in the center, and from there it will send to the other appliance nodes. So it's like the main node is broadcasting the signals to the appliance nodes.
So small question from me also. Is there any limitation from the number of devices on an operate?
At this stage, sir, we have only allocated 3 bits. So there will be, it can only connect 8 appliances. But in the future, we are thinking of increasing the number of appliances that can be connected.
Okay. So we can have one more question if there is. Okay, thank you, Satmini. So we can go to the next presentation. So the sixth paper is IoT-based building energy management system. Authors are Dulini, Akmal Jawad, Vimukti Tharaka, Dinidu, Jeewandara, Professor Udayanga Hemapala. So I think Dulini is going to present.
I'll be presenting, sir. I'm Akmal Jawad and I'll be presenting.
Okay. Okay.
Good day, everyone. Our project is called IoT-based building energy management system. So when we look at the world today, buildings are one of the major electricity consumers, and that amounts to up to 60%. Systems connected to a BMS usually represent a building's energy usage of 40%, and this can come up to 70% if lighting is included. Improperly configured BMS systems are believed to account for 20% of building energy usage. So percentage of building plug loads is more than 60% of total consumption. Efficient controlling can save a considerable amount of energy. Most electricity networks in buildings cannot be easily monitored because the power company provides kilowatt-hour meters only at the main connection. And there are very few applications where monitoring is done in the plug itself. And through our research, we have found that promising pathways can be expected from using IoT and machine learning techniques for real-time monitoring and trend predictions. So our objective, simply stated, is to design a real-time plug-in load monitoring, controlling, and a load forecasting system for an IoT-based building energy management system. And one way how our project differs to other related projects is that when it comes to building management systems, most applications focus on central air conditioning. But we know that there are many buildings, many flats, many offices, many residencies where there are multiple split air conditioners, and there's been a less focus on that, even though the energy usage of that split air condition of those split air conditioners can reach up to 40% of the total energy. So taking that into consideration, we have implemented our project. So taking a look at the literature review, paper cited number 4, it was an IoT application, and the objective was designing a system that empowers building managers to monitor and control power quality on site and off site. And they were able to come up with a energy analytics model to inspect fluctuations and anomaly with sufficient accuracy and performance. And taking a look at paper cited number 7, it was a study of energy management systems and microgrid, and various components, critical aspects, and future trends were studied, as well as the subject of demand side management was studied as well. So when it comes to papers cited number 5, number 6, number 8, and number 9, they speak on different load forecasting techniques, such as time series methods and different machine learning algorithms. And some of the insights, some of the conclusions we could obtain was that ensemble learning techniques turned out to be the best tool. And we can also see in our project how we used an ensemble learning technique for the load forecasting application. So when talking about building energy management systems, this is the overview of the microgrid view of a building energy management system. There can be two types of control. One is the centralized control, and the other is the decentralized control. So when it comes to the centralized control, the decisions related to managing buildings demand and supply are taken centrally, taken through a central control. While when it comes to decentralized control, each building has the independence to take decisions related to managing the building's demand and supply. And when it comes to the demand within buildings, there are two types of loads. One is called controllable loads and the other is called critical loads. Controllable loads are the loads which the building operator can afford to shed, while critical loads are the loads that the building cannot afford to shed. So in our application, we can see that we go for the controllable, we go for the decentralized approach of energy management systems. So this is a building view of energy management systems. So we can see that in each room, we take voltage, current, AC, and humidity measurements. And we also gather data related to occupancy. And this data is sent to the dashboard, and the building operator who uses this dashboard, he has the ability to he has the ability to control the plugs as well as control the AC temperature. So this is, so we saw the building view. This is the room view of our application. So talking about our voltage and control and current measuring unit, we use two sensors. One is the current sensor ACS712 and the voltage sensor ZMPT101B. And using this device, you can monitor as well as control the plug-in loads. This is a Proteus simulation of our voltage and current measuring unit. And this is the Proteus simulation of our AC control unit. So the reason we go for AC control unit is because of a related research done in our university, where they found out that reducing the temperature of split ACs by 4 degrees can reduce the energy consumption by 50%. So, so taking that into consideration, we have designed a device in order to be able to control split AC temperature. So this is a device dashboard communication. You can see the three layers of IoT here. On the right, you have the acquisition layer, and in the middle with the get request and the post request, we have the transport layer, and finally with the processing of the data and the dashboard metrics and the forecasting, we have the application layer of IoT. So when it comes to electrical load forecasting, it can be divided into three. One is the short-term load forecasting, medium-term load forecasting, and long-term load forecasting. Short-term load forecasting deals with forecasts of 1 hour to 1 week. So that is the that is what pertains to our project. And when it comes to forecasting, it can also be divided into traditional statistics models and machine learning models. So the reason why we use machine learning rather than using traditional statistics, if we want to create an algorithm that can predict in high accuracy, machine learning is likely the better approach. But if you are trying to prove a relationship between variables, a traditional statistic model is likely the better approach. Also, machine learning is better at dealing with very complex variables and dealing with errors. And it's also better at dealing with errors. So the major difference between machine learning and statistics is their purpose. Machine learning models are designed to make the most accurate predictions possible. Statistical models are designed for inference about the relationships between variables. So the machine learning algorithm which we used, it was the XGBoost algorithm. And how the XGBoost algorithm works is by building trees based on errors of previous trees. And it scales the prediction of the new tree and adds to the prediction of previous trees. So talking about our machine learning pipeline, we acquire the data, the load data, the weather data, occupancy data, and we pre-process it. And then we input it into the model and we train it. And then comparing it with the test data, we do hyperparameter tuning, and finally we obtain a model of sufficient accuracy. So speaking about our occupancy detection model, it's object detection from real-time video streams, and it was developed using OpenCV library, and it's done by it's based on deep learning and specifically CNN, convolutional neural networks in deep learning. So these are dashboard where we can see on the left-hand side where we can where the sensor data is displayed, and in the middle we can add and on the lower left-hand side we can see the control, how we can control the devices, and in the middle of the dashboard we can see how we add new devices and add new devices in different rooms and floors. And on the right hand side we can see the energy prediction, and below that we can see the different graphs related to the data and the forecasting. So as a conclusion, in this paper, we have proposed a methodology which can be implemented for a building energy management system using IoT and machine learning. We have presented designs for a smart plug-in device with real-time monitoring and controlling of plug loads, a smart remote device allowing temperature controlling of air conditioning units, a dashboard as the user interface which interconnects the different devices, allowing user to monitor and control the electrical appliances. And a methodology for load forecasting was analyzed, where we have identified XGBoost machine learning algorithm as the best fit for short-term load forecasting. So these are our references. Thank you.
Okay, thank you, Akmal. So, any questions from the audience?
IoT-based building energy management.
Okay, any questions from the audience? Yeah, very small questions. What type of microcontroller you use?
We use Node MCUs.
Right. If there is no questions, we can move on to the next paper presentation. So that is techno-economic feasibility of implementing carbon capture and storage technology in Sri Lankan power system. The authors are RM Tushara Damayanti, Kasuni Madhushani, Guruita. Who's going to present?
Sir, Kasuni Madhushani Guruita is there.
Okay, okay. Thank you.
Hello, I'm Kasuni Guruita. So today my topic is techno-economic feasibility of implementing carbon capture and storage technology in Sri Lankan power system. My supervisor is Dr. Tushara Ratnayaka. So let's go into our today's content. So first I'm giving an introduction about the CCS technology and problem statement and the objectives of my research, then the methodology part and the simulation and results, discussion and the conclusion. Before going to the problem statement, I would like to give a small introduction about the CCS technology. CCS technology is an upcoming technology in the world. So this technology is most famous around in the USA, China. There are 3 steps in this technology. The first one is the carbon capture stage. The second one is the transportation stage. And the third one is the storing stage. So in the capturing stage, there are four kinds of technologies that we can use. And mine is the environmental effect. Due to this the technology, how the resources are increasing or decreasing because of this technology. The last one is the estimate the cost viability of the implementation of CCS technology. Let's move into the methodology part. There are 6 steps I have followed in my research. The first one is to determine the most suitable CCS technology. To achieve that stage task, I have used ICM software and get those results. To validate those results and data, I have used the CEB long-term generation plan. With that, I have compared my simulation results together with the CEB long-term generation plan. After that, I calculate the cost of implementing CCS technology in Sri Lankan thermal and coal power plants. Next, determine the unit cost of electricity with CCS technology. Fourth task I have done is calculate the economical benefit of reducing CO2 emission to the environment. After that, the cost benefit to the because of the CCS technology, what is the cost benefit that we can get? The last stage is the economical feasibility of this project. So this is the typical schematic diagram of a possible CCM technology system that is available in the world. Right. The next stage is the data collection and simulation for different CCS technology. As I mentioned earlier, I have used EECon software to simulate these technologies. This is the data I get from the software. As you can see, I have simulated the base case first, then the different technologies in different time. So after that, I summarized all the simulation results and I got some conclusion after comparing different kinds of technologies. As you can see in the first column, it's indicating the reduction of CO2 emission. The next one is fuel consumption. Third one is the water requirement. Conclusions. Coal and fuel consumption are increased. The total requirement of water also increased in all technologies. The solvent and scrubber solid disposed are insignificant for the solvent-based process. The other one is the membrane and ammonia-based capture process are zero in emission due to the filter putting. So these are the main highlight points in the summary. The next one is the results validation part. As I mentioned earlier, I have used a CEB long-term generation plan data to validate these results. So after comparing all these stages and the resource increment and the decrease in CO2, after that I have selected the most suitable technology for each power plant separately. So to do that one, I have given an economical value to the fuel increment as well as the water increment. After comparing all those factors, the Lakvijaya is more suitable. Selected technologies amine. Likewise, all fuel and coal power plants, I have selected the suitable technology. Then that is the end of the capturing part. Now I am moving to the transportation and the storing captured CO2. So in that case, we have to use either pipeline or ship. So when we are transporting, we have to pressurize this captured CO2 into 73 bars. Then it reaches to the supercritical stage and high density. So giving it a property to similar to a liquid stage. So we can easily move using a pipeline or a ship. So if we are transporting 500 to 1000 kilometers, the most suitable transportation mode is the ship. So let's move into the storage part. So in Sri Lanka, as we know, we are having some oil. According to Petroleum Corporation, we are having some oil and reduce. So after analyzing the most suitable oil blocks, we can use M1 block. As according to this diagram, you can see we can use M1 block and the C1 block because those blocks are very much near to the Sri Lanka, right? So if you use those blocks according to this equation, we can nearly the M1. If you use M1 block, we can store around more than 800 metric ton. So if we use C1 block, we can store more than 600 metric tons. So the next one is the transportation and storage cost. So if we use the as I mentioned earlier, if you use ship, because the distance between the storage place and the capturing place is nearly below than the 500 kilometers. So if you use that method, so our cost will be around between $10 per ton if you use it. After summarizing all the cost factors and the technology cost and the storage and the transportation cost, I have calculated the total cost around about this technology. So after calculating all total cost, then I have calculated the generation cost without considering the CCS technology and the generation cost of electricity considering only CO2 transportation storage cost. So if you compare these two values, the total cost in the without CCS technology and with the cost only considering the transportation and storage cost, somewhat we can bearable. The next one is the carbon pricing. So why am I mentioning that one? Because we need money to implement this technology. So to do that one, the carbon pricing is we have to give a value to this carbon capturing technology. So good method is carbon pricing. This is a new technology to Sri Lanka, but other countries are already using this technology. So in that case, carbon pricing is a market-based energy for lowering global warming emissions, but put a price on the carbon emission. So the economical benefit by reducing CO2 emission to the environment, to calculate that one, this is as you can see, the most emissions are related to the transport and the electricity and heat production. So in Sri Lanka, the total CO2 emission around 16.74 metric ton. So if we compare that one, so the around electricity and heat generation, it becomes 6.8 million tons. So if we reduce that emission by 90%, then our carbon tax, the economical value due to CO2 reduction will be $320 million. The next one is the project feasibility. So as I mentioned earlier, we have our total cost is around 2,800 million to achieve this target calculation. That one we have to if we are whether this project is feasible or not. The normal guideline is the generally equity IRR is more than project IRR, and the equity IRR will be lower than the project IRR whenever the cost of debt exceeds the project IRR. So using that analysis, I have take 5 options. The first one is the equity IRR, the ratio is equal. Likewise, I have do my case analysis into 5 stages. So in that case, you can see the most suitable ratio is the 5-year loan project. That is the debt to equity ratio is 75 to 25%. So interest rate should be 4. So likewise, the most suitable option is case number 2. If you are using this kind. However, CO2 emissions from Sri Lanka power sector is only 0.05%. As we know, it is a very, very low amount compared to USA and China of the total global emission. Therefore, we propose that such a huge capital investment would be considered by the decision makers as low emitting country. So we can suggest it, but the decision makers should take care of the decision making. Thank you. These are my references. So thank you very much for listening to my presentation.
Okay, thank you, Kasni. So, any questions from the audience?
Hello, I'm Simla Pitia. Thank you for the good work and the good presentation. Did you calculate the value for CO2 at which the project will be viable? Why I am asking is, with a negative IRR, the project has to be classified as unviable. So you could also calculate either the value of CO2 or the benefit by way of pricing, say, coal power at so many dollars per megawatt hour more, at which the project will be viable. Did you do any calculation like that?
No, sir, I didn't do that kind of that kind of big analysis to the my project. I just take the values and the economical value and compare those two and did the project IR and the equity IR.
Yes, because in general, to conclude that a project is not viable is of course good, because negative IRR means not viable, but it would also be nice to say at what conditions the project may be viable. Maybe a grant, 50% grant for the project investment, or a higher valuation of CO2. So this is a comment.
Yeah, thank you very much. Thank you.
Okay, any other question? Yeah, according to the presentation, I think the increased electricity cost per kilowatt hour is 3.2 rupees in terms of rupees.
That's right, yes.
I hope I am audible.
Sorry?
Hope I am audible.
Yes.
Yeah, thank you, a great presentation, and I'm Mavin. So I just want to get one thing clarified. In this particular study, the authors, I want to know whether the authors considered any sensitivity to particular cost component and analyzed, I mean, how that would affect the feasibility of the study, because if we are to use the negative IRR and the other components will say that this project is not feasible, but in order to give more thorough analysis, have authors considered any of sensitivity effect to the particular cost components?
No, I didn't consider that sensitivity analysis to the cost component and the thing.
Okay, so due to the time limitation, so we have to go to the next presentation. Thank you, Kasumi.
Thank you, sir.
The last presentation, so that is an experimental study on a smart electric bicycle with optimized power pack. The authors are Chatura De Silva, Surani Kausika, Perang Kalhar, Sudar Randubage, Marvin De Silva, Tisal Sajana, and there are 3 other authors as well. Okay, who is going to present the paper?
I'm Chatura, and I will be presenting.
So we can start.
Hi, I'm Chatura Silva. On behalf of my team, I'll be presenting our research, an experimental study on a smart electric bicycle with optimized power pack. Let's start with the scope and objectives. Our scope is to design and study about an electrically assisted bicycle prototype, including hardware, power pack, bicycle computer, physiological information, and the bicycle sensor data. This is the study procedure of our research. First, we recorded the data for heart rate variability, and bicycle sensor data with test rides. Then we analyzed those data and extracted necessary information. Finally, we compare those results to identify fatigue level and verify the power calculation. This is the system block diagram of the bicycle embedded system. There are two main parts in the system. The first one is a bicycle helmet with computer to collect and process riders' data. And the second one is the bicycle computer. It is to collect and process the bicycle sensor data. The helmet and bicycle have real-time communication to update both sides. So bicycle sensor data will send to the bicycle computer. The helmet and the bicycle have real-time communication between both computers. So the bicycle computer sends the processed sensor data to the helmet, and the helmet sends the processed static signal to the bicycle. These are some of the hardware components we are using in our helmet and the bicycle. Following equations used to record and process the sensor data in our system, and I will discuss those results in later slides of this presentation. The power calculation was done by considering a constant speed during the ride. Rolling resistance, slope resistance, and the drag resistance are considered as main resistive forces to the rider. We can get the total required power by multiplying sum of those powers and bicycle speed. Then the work need to be done by the rider is equal to total required force multiplied by the ride distance. And finally, weight of the bicycle should be minimized because it is the dominant parameter in this study. Total work required to overcome the hill is equal to the work done by the man and work done by the motor. Practically, a particular rider can apply certain amount of power for a specified time period. The bottom graph shows one of the examples regarding power and time variation. In here, those two parameters are T total for power and T3 for time. But if the total work is less than required work, we cannot continue the ride. So we should turn on the motor at a time Tm which is well below Tb. The Tm will be decided with the fatigue level of the rider. So finally, we can calculate the power required from the motor using those relations. This is an example of power calculation for 70 kg weighted rider with 50 kg weighted bicycle. And we consider 20% gradient of 200 meter distance while taking 2.5 meter per second speed as the bicycle speed. Then apply those values in the previous equations and we got the total power as 417 watt. So according to the motor power equation, we got the required motor power as 120 watt. So finally, considering the losses, we selected the motor having 150 watt of rated power to continue our research. We did our experiment related to 5 persons on 3 different slopes. This graph shows the power calculation for the different riders in different slope profiles. If a rider can give a power of 200 watt for more than half an hour, 150 watt motor would be enough to assist the rider in the case of 16 to 20% slope. Let's see the experiment results of our research study. These two graphs are related to the last 5 minutes of 7.5 km ride. The first graph is for untrained rider and the brown color line is for heart rate variability. So first rider has higher value of heart rate variability than second rider. This is the first important thing about the heart rate variability. The heart rate variability is having a lower and constant value when the rider is adapting to the exercise or the riding. If the heart rate variability trend deviates suddenly, we can easily predict about the riding condition of a trained rider. We used a push button to record the fatigue during the experiment. The light blue color in the graphs shows the fatigue signal that we have recorded. Here, heart rate variability is rising for a 30-second prior interval before the fatigue event. So if we can turn the mode on considering the heart rate variability, we can assist the rider before he's getting fatigued. From here, we can see the recovery process during the bicycle ride. We can see the heart rate variability is decreasing in the part which is marked in green color. The gray color line shows the bicycle speed. So in the same time, we can see the bicycle speed is increasing, which means the rider is going downward on the slope. Therefore, likewise, if we can turn on the motor on while heart rate variability is increasing, we can expect the same result, which means heart rate variability will reduce and the rider will recover during that period. Next, we considered the cadence of the cyclist and bicycle speed variation for our study. Cadence is the RPM, the pedal, which is a vital parameter in bicycle riding. A rider can lose his cadence in two scenarios. The first one is intentionally stop the ride, or the second one is the rider is getting fatigued. And here we consider about the second scenario. So we can see the heart rate variability is increasing while cadence is decreasing during the interval which we marked as in red color. So at that interval, bicycle speed also reduced. So we can conclude that the cadence data can use to support the fatigue detection. Regarding the physiological parameters, our final target was to consider the motor assist before the rider getting fatigued. So during the experiment, we turned the motor on in different scenarios. Following graph related to no incident during the experiment. Here the yellow color shows the motor speed. So we can see that the increasing trend of heart rate variability is reducing for a moment where the motor is turned on. This means rider getting some recovery. So we can use the recorded data for further analysis related to these fatigue events. Then we can move into experiment results related to power calculation. The following two graphs are taken from the results based on the motor that we have selected before. The person 2, who is 70 kg of weight, had good assist from the motor, like 60 watt of assist, and the other one, his weight 77 kilograms, so he is getting somewhat lesser assist from the motor. So the results highly depend on person's weight, person's fitness, road slope, and many other parameters. So there are more experiments need to be done related to motor power considering the RPM and the psychological data as well. The main objective of the study is to check the motor assistance for slope with lower gradients. The motor assist is sufficient to overcome the additional power requirement for 4 to 6% gradient. As you can see, the average power is somewhat lower compared to the rated power of the motor. You can see that the average power is nearly 60 watt, but our motor was 150 watt. So this is because of the copper loss of the motor. If we get fatigued, we will lose the cadence, which means the motor RPM getting lower, motor copper losses will be high. So we identified two changes to overcome this issue. The first one is to change the motor mounting position. That will help to operate the motor in an efficient manner compared to the current position that we have mounted. And the next one is we need to go for the motor having higher voltage compared to the motor that we are using now, because the motor is 12 volt, and if we can increase the voltage, that will reduce the current for the same power, and losses will be smaller in next studies. Next, we can say that the motor should be turned on before the rider gets fatigue, although he got the support. That will maintain the cadence of the rider. So cadence is the important parameter. So we have to maintain the cadence while assist the rider. Next, the motor assist was around 60 watt during the experiment. So we have verified the motor assist is sufficient for lower gradients like 5 to 6%. At last, we have developed a power pack which weighs less than 2 kg. This power pack includes the motor, mounting brackets, chain, and the sensory items. So this would be a very comfortable for the rider as an additional weight during the ride. Thank you, everyone.
Okay, thank you, Chatla. Any question from the audience?
One thing I noticed, Chatur, is that you presented several graphs which contain heart rate and the bicycle speed and all that. But the vertical axis was only marked with the heart rate. So we couldn't judge what are the bicycle speed, etc. you are talking about.
No, so actually I have marked in the right corner. What are the parameters?
Okay. At one point in one slide I saw you are talking about 5 kilometers per hour. Now there was a number. Bicycle speed. What is that?
Bicycle speed, sir.
But bicycle speed 5 kilometers per hour is normally our walking speed.
Yes, sir. That's because in our experiment, the motor was not enough actually. So we tested for lower gradients.
But how you can't ride at 5 kilometers per hour because it's the normal person's walking speed.
Yes, sir.
How can you ride the bicycle at this speed? That is a separate game.
No, sir. That was because that RPM is low. That's the reason, sir. We have to maintain the cadence to.
In that stuff, you had this heartbeat and also the speed coming and where we are going on a declination. It seems that is you are going downhill and so speeding up.
Yes.
So what kind of speeds that you are talking about there? There was a graph where the person is going downhill.
Yes, sir. That means
What kind of speed? What kind of speed you are talking about? 30 kilometers per hour?
Yes, sir. Yes.
About that.
30. Sometimes about the 30 kilometers.
Yeah. So at that point, what is the wattage?
At that point, we are not assisting, sir, because we are not taking the readings because we assist only when the rider getting fatigued.
Okay. Then when he going uphill and
yes.
So. Okay. That's all from me. Okay. Dr. Wijekoon.
Yes, sir. So you are 5% inclined with 60 watt assist. For what is the weight of the person?
It was for like 70 kilograms.
Okay, so that's all from this session. So thank you very much for all the authors. So we can
thank you, sir.
Wind up the presentation.
Thank you very much, everybody. Yes, we will close the session. And before that, we will thank all the presenters and also the audience for remaining with us. And so we encourage all the presenters and wish them all the best for your future research as well as publications. Thank you. So we'll conclude the session. Thank you, Dr. Wijekoon also.
Thank you very much, Professor Wijayapala and Dr. Wijekoon. At the end, since we are concluding the session, shall we take a photograph?
Yes.
If all of you can turn your video feed on.
Okay, thank you, Eva.
Thank you. Okay, so I have mentioned in the chat as well, you can access the presentation videos and then the manuscripts, relevant manuscripts using the program schedule at the end of the day. Once the conference, all the conference sessions are concluded using the given link. Thank you very much, everyone. You can join the technical sessions too now using the given links.
Thank you, Dr. Rosara.
Thank you, Rosara.
Thank you.
Professor Wijayapala, I will make you the host and then leave the session. Dr. Wijekoon, I think Professor Anura left the meeting. I will ask him to join back. Dr. Wijekoon, I'm trying to contact Professor Anura, but still couldn't contact him.
1 minute. Dr. Rosara, we are just talking about this, and we will, separately discuss and evaluate. Okay.
Okay. Then Dr. Wijekoon, you can end the session.
I'm talking with Professor.
Okay, I have assigned you as the host, so you can end the session.
Okay.
Okay, thank you very much.